Hello, my name's Nathan Hadaway, and this is my Physics 2 Lab 3 on circuits. So what is this lab? Well, this is a lab where we took a battery, a couple resistors, wire, and a light bulb, and we hooked them up in different circuits in series and parallel and then used multimeters to test the voltage and the current, the change in voltage on across different across different areas of this circuit and the current through different loops and whatnot. Um, we took note of all the data that we collected, and then we saw if this compared to the real world in the physics equations that we see in our textbooks. I'll get more into those exact equations on the next slide. The system and the surroundings is a little strange to define. I defined it here as the entire circuit is basically a closed system without the surroundings being, anything else in the universe. But the surroundings aren't really affecting the system that much. You could also think of the system as um, everything except for the batteries, which are kind of um, putting the energy, putting the voltage, putting the um, you know, which would be acting on the system as in the rest of the loop. Um, so yeah. So what is this lab trying to prove? Well, mainly it's trying to prove this first equation, V equals IR. This is voltage equals current times resistance. This shows up countless times in our lab. Here in the first bullet point, I kind of explain the uh, the first place that it comes up. You can also see my notes from the lab on the right hand side. So a couple ways that this voltage equals current times resistance equation comes up is we found the voltage from the batteries. I mean, there were 1.5 volt batteries, two of them in parallel, so it was 3 volts, um, or in series, not parallel. My bad. So it was 3 volts, and then we had two resistors in series that were of 140. 100 was one of them, and 47 ohms was the other one. Resistance. So then we calculated that the um, current through this loop we expected would be about 20 milliamps. In reality, we found it to be about 17 and a half. And we did find that this was pretty constant throughout the entire current. It didn't drop from, you know, before the 100 ohm resistor to after the 100 ohm system. Whereas this was different with not velocity, with um, voltage, which did drop after each resistor, which you can see we notated that. So yeah, it shows that voltage changes over resistors in a loop. Um, Current is constant through a loop. We saw that from the fact that we tested different parts of the loop and it still stayed at 17.5 milliamps. And this V equals IR equation comes up many times. We saw it again when we bypassed the 100 amp resistor. So basically we took it out of the equation. So you'd expect, resistance goes down if not velocity. Why am I voltage? If voltage stays the same because of the same batteries, that resistance going down means that current has to go up, which is what we did see. We saw the current going up to about 18 milliamps. And there's all this data here. So we really did try to prove this velocity equals current times resistance equation, physics equation. Now, some frequently asked questions are what would happen if you tried to charge a capacitor with no resistors? Now, at a glance, this might seem fine, but actually, this is what happens oftentimes when resistors um, get short-cutted. You get short circuits. That's what they're called. I don't know why I blanked on that, but theoretically, this would, zero resistance would mean that there'd be an infinite current with any voltage, which would instantaneously bring the capacitor to a full charge, to be in equilibrium with the battery and whatnot. And however, in real life, this doesn't work that way when you short circuit a resistor. Usually it leads to material breakdown and high temperatures and sparking and fire and bad things because the tools aren't made for infinite current or at least extremely high current. Thank you for listening.